Yeah, so we're developing this website, BioniChaos.com. Like, so everything we do in the streams eventually ends up on this website that you can check out yourself. Yeah, yesterday we were streaming. We're doing like, yeah, a lot of, yeah, it's BioniChaos is the handle. Yesterday we're doing this interactive Dissonance Viewer. So this can actually play music thing. So like an AI that plays music. Yes, we do. You can choose intervals 2 notes or 3 notes. So 3 notes turns it into a 3-dimensional chart. How cool is that? So you have essentially the ratio for F, whatever frequency, frequency 1, then ratio of frequency 2, frequency 1. So you can place. So essentially, if you stand the line, well, the reason we were doing it is to do with how your hearing works, how your brain is processing hearing. Because yeah, we have a bit of a thing for hearing, you know, research, whatever stuff. Yeah, so if you stay on that line in the middle, it should sound better to you. It should sound in tune. Whereas if you diverge from the midline, it will sound off. No, maybe. Wait, no, maybe those lines. No, I think those lines as well. This is where it should sound in tune. Yeah, we're talking about this font sensor dashboard. We need more work on that. We'll do it later. Yeah, so that's the turning brainwaves into music. So we covered it yesterday. I don't know if there would be anything else to cover on this. EEG to music. Yes, so what else? Let's open Visual Studio Code. Yeah, we had the EarDraw. What's this evolution? Oh, it was some of those what's called emergence games. Yeah, emergence. So we have a lot of this. Yeah, we have the game of life going on the side. Yeah, game of life. Someone says it's the thing that we are playing right now. Well, not unless you are AI. Well, then there is still emergence. So AI, like a language model, will have an emergent behavior because it's like basic rules, whatever, fairly basic neural network. But to you, it sounds as if it, you know, generating human-like output. Where was game of life? Yeah, game of life. Yeah, so that one's still running. Obviously, we could do a better version of it. This one's a bit like it's a modification of the original one. You can add rock and water and sand, and the main thing about this one is that life will actually continue being generated around water. Yeah, how good is that? Water. Yeah, so it will keep generating life around water. Yeah, so what we're doing game of life. Game of life. So it kind of got stuck. Got stuck on us. Yeah, interactive life simulation. Yeah, you have like keyboard shortcuts for it, but also it's a modified version. It's not like the original. One. So we're streaming everything we do eventually ends up on the website. You can check all the development process happening on YouTube. Yes, so you can see me, you can see the live game of life simulation. We just use it as testing, whatever. This one was developed like a while back. Yeah, by one of the AI models. I don't remember which one it was. Probably was like GPT 3.3 or 3.5 or something like that. It was. Now it seems like his prehistoric times. Yeah, so I did this like pixelated thing. It's still running on the site, BioniChaos.com/live. You can check it out, play with it. Yeah, you can add sand. Sand just drops down. For some reason it stays on water. Why does it stay on water? I don't know why it stays on water. Yeah, if you place it inside water, it's just floating. I don't know. Rock just stays midair. Makes sense, right? That sense, sand is falling down and water just hovering. We can do anything in virtual space, so it is what it is. That's just what the board have decided to make. What else we have? The interactive evolution simulation. The reason I put showed the game of life is because we're actually looking at this interactive evolution simulator. So this one, yeah, got too many things going on, but essentially it's some sort of life emerging thingy, life emergence of life. You have different scenarios. You have go east, barrier challenge, corner seeker. So you have this. It's a description. Interactive application is a simplified model of evolution by natural selection. Yeah, it's a bit of a stretch. It's much more basic. Inspired by a video by David Randall Miller. You're observing a population of simple digital creatures. So they're not cells or anything, they're creatures. Okay. Demo complete. What? Yeah, I don't like those pop-ups on the screen. I have to get rid of them. I don't know why the bots are always resorting into adding those. So each creature has a unique genetic code that defines the wiring of its simple neural network brain. So they have a brain. And yes, you can change the population size, mutation. I don't know what mutation does. Speed. Okay, speed works. Speed works nicely that it doesn't actually like re-render. It well, why is it jumping like that? Every now and then starts like another simulation. Sorry. Right. So what else do we have? Speed, genome length. So we have the length of the genome. It just respawns the visualization, but it doesn't seem to do much else. Well, at least I don't have the audio. Let's audio. You might want to close your ears. Well, I can't hear it. Okay. No, there's there's another challenge, a barrier challenge. Yeah, so I remember, yeah, that was from the video. Yeah, barrier corner seeker. Let's try that. Anyway, it's they're meant to all end up in that corner, whatever, top left. The corner in every corner there's a corner. So they're just seeking, the creatures are seeking a corner. They're doing a good job. Oh, there's like a time limit. Okay. There is audio, so that's working. And you can change the number of internal neurons. So supposedly, if you increase it, they become smarter or something. Maybe. Genome length. Not sure what that does. So it's running a simulation for like a limited period of time. There's 300 steps. Right, so it's doing steps out of 300. Do we need to be able to change the number of steps, essentially let it run for longer, or keep it as a hardwired limit for the number of steps? Yeah, I need to limit the browser. Yeah, the audio is only doing when the step counter resets. So there's a audio feedback. Can reset manually. Can play demo. Anyway, I don't know if what's the future direction? Over many generations, you can witness the population adapting to its environment. Successful traits are passed on and refined, while unsuccessful ones are filtered out, leading to the emergence of complex and efficient strategies from very simple rules. Well, yeah, so as opposed to Game of Life or something, it's not immediately obvious where the emergence is happening, or if it's happening at all. We had another emergent behavior, was the bird flocking thing. Yeah, Boids, they're called Boids. So I don't know, just a name. But you can, so in this one you can select the Boid count. So let's make it whatever, 200. Cohesion. So cohesion makes them fly closer to one another. There's one lost. There's a lost Boid there. It's trying to find its mates. Yeah, we're covering Boids Flocking. So we're just doing like examples of emergent behavior, which the obvious one is Game of Life, which we have our own modified version. I can empty cells as well, and you can essentially turn like generate like incubators. So you can make an incubator out of a rock, fill it up with water, because water is generating life. Someone says rocket science. Well, no, it's not rocket science. Water, and the life will be generated around water. There is rock life. I can what? How does that? Right. So it's only so the basic rules are that they are generated around other life. But in this case, the modified version is that it can be generated around water as well. Yes, you can generate life anywhere in empty space. It has to be around other life or around water. What else we've got? Yes, let's imagine behavior. The Boids. Yes, we have number of Boids, cohesion, makes them fly, speed. Well, that's obvious. But again, the speed, yeah, I remember it took some time to actually get it to adjust the speed on the fly instead of like it's called restarting the simulation. It's actually, you can change the speed on the fly, so that's nice. And what else we have? Alignment. What's the difference in alignment and cohesion? So cohesion, they fly closer to one another. Alignment. Right, there's more randomness to the thing. Yeah, so that's that. We have live Boids. Yes, this interactive evolution. Yeah, obviously it's an attempt to make it like much more complicated, but it's not really working. What does it say? Demo complete for? Yeah, again, I don't like those pop-ups on the screen. They're not great. Anyway, we have still Game of Life going. There's probably not enough incubators. We can add more incubators or something to make it a bit more interesting. So you have to actually make like a rock bed. Yeah, if you keep it like this, I think water will actually leak out. Pop-ups are bad. I don't know, the AI is always resorting to using pop-ups on the screen, but we're always trying to tell it to get rid of them. Okay, now we're showing the waveform. So that waveform is my heart rate. Can you believe it or not? Well, it does work if you don't move and control the light in the room. Actually showing you my heart rate. How good is that? Okay, so we have this thing that measuring heart rate using a web camera. So we have some two simulations that are essentially showing how it works. So we have this one that just have your face as a model, and then we have another one that's showing the synthetic data. So they're kind of both useful. One, yeah, so you have a Eulerian Signal Processing Viewer simulating the core principle of no contact physiological signal extraction. So we have an actual application that's working. You can see it. It's on the landing page. Oops, not this one. The camera. Yeah, will only work in my other browser. Yeah, so this one you can change noise level, signal strength, and the fundamental frequency, so which in this case is simulating beats per minute. So your blood pressure, not pressure, you know what I mean, the heart rate, sorry, heart rate, not pressure, not doing pressure, even though you could probably do pressure from PPG, from light changing on your skin. Maybe sometimes there might be this, it's called a dichrotic notch that you meant to be able to see sometimes. So it's also with PPG, simulating PPG. Yeah, that would be like a dichrotic notch there, which actually out of that supposedly you could calculate systolic, whatever, but probably not. Well, because it's noisy, just because it's not always there. Just because it's not always there. Yeah, so same with a smartwatch that does PPG, or the finger sensor, which is better. The finger is shining light from both directions. So, sorry, the transmitter and receiver are opposite to one another, so across the finger, so you get a better signal. Signal-hallelujah. PPG. Yeah, this one here. Yeah, so this one shows like, yeah, skin tone, things like that. So it will affect the face recording as well of the webcam. Yeah, it's highly sensitive to the light in the room and stuff. So sorry, so we're jumping around many different things, but essentially what I was trying to say, let's close this. Let's close game of life and stuff. Yeah. EG, we'll leave it EG. I'll just go to the landing page there. Yeah, so this one shows a simulation of your face, what your face meant to be doing when your blood is pulsing through it. You can change the magnification, so it should, I don't know, you can barely see it, but yeah, the color there is changing. It's subtle, it's there. Yeah, you can amplify probably to like 1000 or something. It's a simulation, so it's fake. Just to, you know, to make the point clearer. Then we actually have the actual signal, so that's what you get on the output. That will be the green light extracted from your face and the minor changes in it that you'll be looking at, and the change going up and down will indicate the heart rate. So this is again obviously synthetic. This is what will happen when your heart rate is slowing down or increasing. And yes, there will be noise, so you can simulate noise, and signal strength and sonification as well. And the one you see where you see my face, whatever, that's the real deal. That's how it will work in reality. Reality. Yes, in reality, if you stayed, well, first we'll probably need more light. Let's do a bit more light. And if you didn't move, keep testing this one. Keep testing it forever. Yeah, so that's clear PPG there. You know, me talking. Yeah, there's a clear peak there. It's a strong signal, high quality signal. I don't know why the quality, it says quality fair, but reality is the signal is actually of very high quality over there. Yeah, when I start moving and stuff, it you know, drops, and that's okay. And you can compare it to a smartwatch with a Garmin in this case. See what your actual heart rate doing if you're still alive. Let's see what reading we get. Yeah, so we get a 70 and 72 on the smartwatch. So it's kind of comparable, roughly comparable. My my heart rate on a video camera recording, and my smartwatch is showing about the same value. And we can turn sonification on it as well. We can turn sonification. Actually listen to it as a form of meditation. We can listen to it as a form of meditation. We can listen to it as a form of meditation. Where's the... yeah, enables. Yeah, so now we get it as feedback. That's what it sounds like. That's what it sounds like when I move. So it can be a motion. Pretty much any sensor can be a motion detector, isn't it? And when I stop moving, it should be more, well, essentially sound more like my heart pulsing. But essentially it's the color of my skin changing as the blood is pulsing through my head. So I wonder, obviously could use it for meditation as a what's called neural feedback thing. I don't know if I can still talk without... The number is jumping quite a bit, but it's like 70? Yeah, I get 70, 72 or something. Yet if you treat it as PPG, if you process that signal as PPG, that dichrotic notch essentially looks like potentially it's sometimes there, maybe, but yeah, it will look like this, like that notch there. Yeah, it looks a lot like the dichrotic notch. Well, problem is it's not always there, right? So yeah, so you can hear, so we can do like a meditation with this thing. Trying to. Does it work? Well, it doesn't really work. Well, I mean, it works in the sense that it does something. It doesn't work that I cannot actually reduce my heart rate on request. I'm sure a yogi will be able to do it. But as you can hear and see my heart rate, that peak there is the measurement. It's the calculation. Showing 70 beats per minute. My smartwatch showing slightly higher, 74, but it's like close. It's like close enough. We're doing meditation. Have neural feedback. Oh, that's a bit weird. Yeah, we kind of keep testing this thing. Kinda keep testing, because eventually something will give. $77? Yeah, watch says 78. I have to do it for longer and longer, hopefully. Hopefully we can do it for longer and longer. We can do it for longer and longer. We're doing meditation. We are doing meditation. We are doing meditation. Using our heart rate. While doing meditation, I was trying to see if that diachrotic notch is there or not. I don't know if it is. I don't know if it is not. I don't know if it is. I don't know if it's not. What do I do? Someone's asking what do I do? What do I do? We create web applications like this one. You can see me measuring my heart rate using a web camera. So you can hear it and see it. Well, you can use it on yourself if you go into that URL, what's called BioniChaos.com, face blood webcam. Yeah, so we're making web applications, turning biomedical data into games, into interactive web applications / simulations. Because I can tell if the quality of the recording is good or not, so I can tell that much. But I don't know. I can't tell if from the sound. I cannot. Oh, now I moved my eyebrow, so the signal quality went down. So that's okay. That's as expected. It's a feature. It's not a bug. Yeah, so just a reminder, everything we do is eventually available on BioniChaos.com, so you can go check out the website. There's tools like this, like the robotic prosthetic arm interactive simulation, and many, many more. Let me know if you have any questions. Yeah, if you into science, it's probably a good place for you to be. If you are in data science, it's even better. If you are into biomedical data science, it would be amazing. Everything is available on BioniChaos.com. Yeah, we have all sorts. There is all sorts. This is all based on science. It's actually based on a bunch of papers and stuff. So it's not what you think. There should be some papers cited, or maybe it was just, yeah, it's all generated with AI and stuff, so, yeah, just so you know. Just so you know, just so you know. We're generating everything with AI. Yeah, so let me know if you checked it out and have any questions about it. I'm more than happy to take any questions. The questions essentially will be turned into prompts eventually. So you will ask a question, it will be turned into a prompt, give it to one of the AI bots, and everyone's happy. So no one gets upset. No one is being diagnosed with anything. Someone is trying to diagnose me with something. That's okay. I mean, especially if they're qualified for it. Yeah, if you're like a psychologist, psychiatrist, any medical professional, more than happy for you to go for it and practice your magic skills while we're doing something useful, like this magnet web application simulation. Magnetic web application simulation. So yeah, go check it out. It's all, everything we do is on the website. You know what website it is, of course. I need to tell you. In this case, it's BioniChaos.com/magnets. You can try the simulation. One of the better ones we made. Well, the absolutely best one is this one here. It's probably the best one we made so far. It's actually recording your heart rate using a web camera. And you can enable sonification, so I can actually hear my own heart rate and do like a meditation on it. Well, whatever it's called, neural feedback. Is that what it's called? I think so. I think that's what it's called. I was asking, what is it I do? So yeah, a PhD in biomedical engineering, we're working on cochlear implants, also called a bionic ear. So it's a neural stimulation device implanted into your ear to make you hear again. Yeah, someone's doing sign language, that's right. We actually did tools. We did a poor attempt at making a tool that will translate sign language into text, or ideally audio and stuff. But yeah, there's actually Google doing that work. They have a project on it, so they actually have recordings of people signing. There was a big Kaggle competition around it, but my understanding is that the scores weren't great. So I make like web applications like this, like basic stuff where we take physics. Well, I mean, physics simulations are good because you can quickly see what's what. So this is like a magnetic playground. So I'm using AI to build those. So those are all built with AI. So it's all whatever vibe coding. So I just talk to bots. They build stuff for me, and everyone's happy, except people who, for whatever reason, despite AI, really hate AI's guts.
Welcome to the Deep Dive. We take fascinating concepts, sort of strip away the jargon, and get straight to the impactful insights. Today, we're diving into something that, well, it underpins so much of our modern world. Think about how your phone processes signals, or even the rich sound of a symphony. We're talking about the Fourier series. Now, it's a powerful mathematical idea, and yeah, at first glance, it might seem pretty abstract. But we're going to explore how it becomes surprisingly tangible, almost, dare I say, intuitive, thanks to this really incredible interactive simulation we found.
And that's exactly why it's worth digging into, right? In a world just full of information, sometimes too much information, the Fourier series offers this really profound tool. It's about deconstructing what feels like overwhelming complexity into simple, understandable components. Gives you a clearer lens to view a very noisy world.
Exactly. So our mission today is to demystify some of that elegance. We're doing a deep dive into the Fourier series interactive simulation and explorer over at BioniChaos.com. Our goal really is to unravel how this brilliant tool takes a concept that can feel academic and makes it vibrantly real. It lets you visually grasp time domain signals, their frequency components, and these kind of mesmerizing visuals called epicycles.
Yes, the epicycles. That's essentially how you see those simple sine waves combining step by step to create the final signal. It's quite something.
It really is. Okay, so let's unpack this a bit. For those maybe familiar or needing a refresher, what exactly is the Fourier series at its core?
Well, the fundamental idea, the really profound assertion, is that any complex repeating signal, anything periodic, can be built, or you could say deconstructed, using just a combination of simple sine waves, nothing more.
Which is kind of mind-blowing when you first encounter it, that hidden order in things that seem chaotic. Right. And as you remember, each of those individual sine waves in the sum, it's defined by three key things. You've got its specific frequency, that's how quickly it wiggles, basically. Then its amplitude, how strong it is, its intensity. And finally, its phase, which is just its starting point in the cycle, its offset.
And what's really illuminating, I think, is how this seemingly straightforward idea can describe such immense complexity. The source material we looked at uses this great analogy. Think of the final intricate waveform, maybe a sound wave, as a finished dish.
Okay, like a recipe.
Exactly. The individual sine waves are the ingredients. Each ingredient has a specific amount that's its amplitude and a particular type that's its frequency. It's this surprisingly elegant recipe for constructing almost any repeating pattern you can imagine.
That's a great way to put it. And this interactive simulation from BioniChaos.com, well, that's what truly brings this concept to life. It doesn't just tell you about the theory, it actually lets you see it and even hear it happening.
Yeah, it's not just reading the recipe, you're watching the ingredients mix, you see the dish being prepared right there.
Which is just so powerful for learning, isn't it?
Oh, absolutely. When you're grappling with these, abstract mathematical ideas, visualization is often the fastest way to really get it. It cuts through a lot of the mental noise, helps you connect the dots much faster, which, let's face it, is key to absorbing a new knowledge without just feeling totally overwhelmed.
Definitely. So let's walk through it. How do you, the listener, use this simulation to explore these ideas? When you land on the BioniChaos.com page for this, you'll see a collection of presets right there on the left. These are pre-built signals you can just load instantly. You can select classic waveforms, things like the square wave, the sawtooth, the triangle. And it's genuinely, astonishing to watch how these sharp geometric shapes, with their sudden jumps,
Yeah, really abrupt change.
are built entirely from smooth, continuous sine waves.
Yeah.
That's the insight, right?
Yeah.
Even something seemingly unnatural like a square wave used in computing.
Is fundamentally just a symphony of smooth, natural sine waves added together.
It shows how things that seemed really different, like music and digital signals, are actually built from the same mathematical language. It's pretty cool. And beyond those classics, you can explore musical phenomena. There's beats, which is great. It visualizes the interference when you have two frequencies really close together. You see that wavering pattern.
And you can hear it too, that wah-wah sound.
Exactly. Or you can select three-tone chord and literally see and hear a simple musical chord being built from its parts. And if you want to see how richer sounds, richer timbres are formed, you can check out complex tone or 2 Hertz plus 3 Hertz. Shows more complex combinations. Now, the interactive controls are also really powerful. There's this drawing speed slider.
Ah, that's a key one.
It really is. It directly controls the passage of time in the simulation. So if you drag it slowly, you can really watch those rotating vectors. We'll get to those, build up the final shape bit by bit. Or if you just want to sit back, hit auto demo. It'll cycle through the waveforms for you, animating everything.
Kind of like a guided tour.
Right. But for that real aha moment, I think experimenting with the audio toggle is just incredibly illuminating. This lets you hear the signal you're seeing.
Yeah.
Each frequency component gets mapped to an audible pitch, and its amplitude determines the volume. It directly connects the math, the visual, to the sound we actually perceive.
That audio toggle, it really bridges the gap, doesn't it, between the abstract math and something, tangible, something you experience directly. It turns what could just be a visual exercise into something sensory. So thinking about that connection, what's maybe a surprising real-world thing that this clarifies for you?
Well, for me, it really drives home that when you listen to, say, a musical instrument, the richness or the timbre isn't some kind of, magical quality. It's literally just a specific blend of simple sine wave overtones stacked on top of the fundamental frequency.
The recipe again.
Exactly. Hearing a square wave being built, realizing how harsh and buzzy it sounds, yet knowing it's just made of smooth sines. It really makes you think.
How often do we hear complex sounds without realizing they're just these combinations of simple underlying waves?
Precisely. It's like hearing the recipe come to life. Okay, now let's dive into the core of how this tool creates those moments, those insights. It's got these 3 interconnected panes, right?
Yes, 3 main windows or views.
And each gives you a different perspective, but they all work together, showing the same information, just differently.
Precisely, yeah.
So at the top, you've got the big one, the time domain pane. This is probably the view most people are familiar with. It just plots the signal's final amplitude, its strength, up and down against time, moving left to right. And there's a little white dot that traces the signal's value as it's being generated. Standard waveform view, basically.
Pretty straightforward.
Then below that, bottom left, is the Epicycles pane. Now this, for me anyway, is the real heart of the simulation.
I agree. That's where the magic happens visually.
It is. You see the Fourier series dynamically at work.
Yeah.
What you're looking at is a series of rotating arrows. The term is phasers.
Right, like little spinning clock hands.
Kind of. And they're chained together head to tail, starting from a center point. Each one of those arrows represents a single sine wave component from the recipe. Its length tells you its amplitude, how strong that component is.
Longer arrow, louder component.
Exactly. And its speed of rotation tells you its frequency. Faster spin, higher pitch.
Makes sense.
And the truly cool part is how the tip of the very last phaser in the chain traces out the entire waveform in real time. What it draws perfectly matches the graph in the time domain pane above it.
It visually performs the addition of all those rotating sine waves.
Yep. And then finally, bottom right, you have the frequency domain pane. Think of this as the static view, the signal's recipe card, or its spectrum.
The list of ingredients.
The perfect analogy. The horizontal axis here is frequency low to high. The vertical axis is amplitude weak to strong. Each bar you see standing up in this pane represents one single sine wave component needed to build the signal.
And the taller the bar.
The more that specific frequency contributes, the stronger that ingredient is in the final mix.
So if we really connect these 3, they're not just separate displays. As you said, they are this unified dynamic system. It's quite elegant. The frequency domain gives you that list. Frequencies, amplitudes, static,
The recipe.
the recipe. Then the Epicycle's pane takes that recipe and brings it to life. It dynamically sums those components as rotating vectors. You see the process of creation.
You watch the dish being made.
Exactly. And then the vertical position of the final point in that Epicycle chain, when you plot that over time, well, that creates the exact graph you see in the time domain.
Boom. The finished waveform.
It's a complete circle. From ingredients to mixing to the final result, it really offers this profound sense of clarity about how it all works together.
It's just an incredibly clever piece of visualization.
Yeah.
And it's exciting that it's apparently an ongoing project. The creators mentioned possible future updates that could, deepen the understanding even more.
Oh, like what?
Well, imagine being able to just draw your own custom waveform right on the screen.
Wow.
And then have the simulation instantly compute its Fourier series, show you the epicycles and the frequency spectrum for your drawing.
That would be fantastic. A real sandbox.
Totally. And they're also thinking about more advanced controls, letting you tweak phase, amplitude, frequency directly, plus maybe adding more educational content, even the math derivations for those who want to go deeper.
Yeah. Those features, especially the drawing part, hold immense potential. Being able to directly manipulate things and instantly see the graphical and the audible results, that would turn it into an even more powerful interactive lab for just exploring and discovery.
For sure. So wrapping things up, we've taken a deep dive today into the Fourier series. We've revisited how this fundamental mathematical idea lets us deconstruct really complex signals, sounds, images, electrical currents, whatever, into their basic, simple sine wave part.
They're building blocks.
They're building blocks, exactly. And crucially, we've seen how this simulation from BioniChaos.com makes that whole abstract idea incredible, accessible, visual, and even audible. We hope this deep dive has maybe offered some new perspectives or perhaps strengthened your understanding of this really fascinating and fundamental concept.
And maybe, just to leave you with a final thought to mull over, consider how many other seemingly complex things in our world, maybe beyond just sound or signals, might also be broken down into simpler fundamental components. If only we had the right lens or the right recipe to view them through. This kind of thinking, breaking down complexity into its building blocks, it's a powerful tool that you can apply in so many areas, really.
That's a great point. It really makes you wonder about the hidden recipes everywhere, doesn't it?
Yeah. We
definitely encourage you, head over to BioniChaos.com, find the Fourier series simulation, and just play with it. Explore it for yourselves. See what connections you make, what insights click for you. Until next time on The Deep Dive.